Okay, so notes about the packet manager itself. It's written essentially, with some caveats below, entirely in Wolfram language. There used to be a time when the packet manager was written in Java. Many, many, many years ago, it was written in Java. One of the main reasons for that is that some of the functionality, the internet functionality in particular, in Mathematica, used to rely on Java. There was no curl link in Mathematica back then, and all downloads and things like that in the system were done via JLink calling into Java. So it made a little more sense many, many years ago to write this in Java. Maybe I thought it would be faster written in Java, but quite a while back, it was rewritten in Wolfram language. There is one component, the extract Paclet archive function, the thing that unzips .paclet files. That is written in C using library link. And there is still one tiny piece written in Java, which is the create Paclet archive function, the thing that packs a directory of files into a .paclet file. Okay, so what do I consider good Paclet style? Well, I've got bad and good here. Bad is a strong word. It's really more like old and new. The old style of Paclets, which you'll still see today, the head is Paclet. This is what the the contents of the Paclet info file, right? The head Paclet. We had the left-hand sides of the rules were symbols, and it was sort of a a metadata thing, or in Wolfram language, but kind of a metadata that described a Paclet. The modern style, this is uses Paclet object as the head. It's perfectly fine to use pacletinfo.m. The vast majority of packets in the system use .m. But .wl, as you all know, is the file extension that we are moving towards. So people creating Paclets should use .wl. Another thing that you'll see a lot of is the old Mathematica version field. It's called Wolfram version now. And of course, Packet object, the contents of a packet object expression is an association. You have strings on the left-hand sides of all rules instead of symbols. And this modern Paclet info file format is understood by all versions back to 12.1, where we introduced this new format. Versions older than 12.1 do not understand this new Paclet object style of file. So if for some reason you need to write a Paclet that has to work back in 12.0 earlier, you do have to use the old style. All right, so what's allowed in a Paclet info file? Paclet info files are not intended to be general Wolfram language expressions. They're not intended to have, for example, executable code in them, right? They're really sort of metadata in Wolfram language format. When the packet manager reads a Paclet info file, it's not loaded in a standard way. And so you should never call get on a Paclet info file. Now, honestly, using the new Paclet format, you could call get on the vast majority of Paclet info files, because they are literally just a expression in the precise format that they will become when loaded by the Paclet manager. But you shouldn't rely on that in general. So really don't call get on Paclet info files. There's really no need for that. They can contain simple things like lists, association, rules, strings, that sort of stuff. And then some special symbols like automatic, none, manual, a few things that are known to the system already. And you are allowed to have a few Wolfram language functions in them, mostly pattern type functions like alternatives and except. So for example, if you're writing the system ID specification and you want to say that this Paclet, system ID arrow except Windows, something, right? That's legal. That would specify that this Paclet is visible to all system IDs except Windows. So for convenience, there's a few symbols that are allowed in Paclet info files, but those are rarely used. So extensions. Extensions are really the core of the Paclet system. Extensions are the means in which a Paclet tells the Paclet manager how this Paclet extends the system. It tells the Paclet manager what resources this Paclet has. And there are a number of different types of extensions. They're listed in that tutorial. You can also write custom extensions, which is a powerful technique, which is also described a bit in that tutorial. But for our purposes here, we're talking mostly about the kernel extension, because that's really what's relevant for people who are writing components of the system. Typically, they have only or mainly kernel files. So let's look at this Paclet expression. Every Paclet has to have a name and a version. You can have up to 5 dot-separated version fields. Now, the comments in green are sort of top-level rules in the Paclet info file. So this Paclet says, I only work in those system IDs. And it says I only work in Wolfram version 13.1 and later. Now, the precise syntax that you can use to describe your Wolfram version requirement is documented in that tutorial. Paclets that don't match, systems that don't match the system ID and Wolfram version that this Paclet requires, the Paclet will be invisible. Paclet Manager will not load this Paclet or let you see it. So here we list a bunch of extensions. Blue comments are extension level comments, right? So this first kernel extension, a kernel extension tells the Paclet Manager, I have kernel files. You list the context that you provide and some other information. Now, extensions have a root. And the root is the directory, the subdirectory within the Paclet in which the files that belong to this extension live. Most extensions have a default root, like the default root of a documentation extension is a documentation directory. And the default root of a front-end extension is a front-end directory. Kernel, the default root is not a kernel directory, but that is for complex reasons of backward compatibility with older style Paclets, with older style applications. But virtually every single Paclet that has a kernel extension should have a root of kernel. It's good style to put all of your files that belong to a certain category of functionality in a subdirectory within your Paclet. So this is a typical kernel extension. It says root our kernel, and then you declare some contexts. It says, okay, my Paclet has these contexts. Paclet Manager, so whatever you call needs of some context name, the Paclet Manager looks up and says, do I know of a Paclet that claims that it has that context? And that's what you're listing here. But the important thing here is that you can also have things like Wolfram version and system ID in individual extensions. And this is a very powerful technique. It allows you to have one Paclet that has components, that has resources for different versions of the system in the same Paclet in different subdirectories. So here, for example, this Paclet says, well, if I need a special version of my code for version 13. And so you, rather than having some if statement in your code that says, if version is greater than 13, do this, otherwise do that, you can just have a declarative style where you just say that for Wolfram version 13, look in the following directory for kernel files. And then is your typical library link extension. If you have Wolfram library link libraries, you can literally just put library link as your extension. As long as your Paclet conforms to the standard directory layout for library link libraries, which is a folder called library resources and then a system ID subdirectory, things will just work. And again, the conventions for this are documented in that tutorial. And similarly for documentation, if your Paclet has its own documentation, you could typically just have one word documentation extension as long as the layout of your documentation files conforms to the standard layout for Wolfram documentation. So auto-updating Paclets. Paclets can declare themselves to be auto-updating. And that is just this rule, auto-updating true. You will also see the older style, which is updating arrow automatic. Back in the day when we thought there might be multiple types of updating, it was updating arrow something, but now it's just auto-updating arrow true or false. But of course, false is the default, so you wouldn't normally see that. So important things to remember about, and we have a ton of auto update Paclets in the system, and that's a good thing. It's a very nice feature, but it's important to understand that auto updating occurs at one precise point, and that point only. And that is the point in a session when the Paclet's context is first requested with get or needs. And honestly, it's actually, this is not really true. It's not, it's actually find file. The first time a resource from the Paclet is found with find file, which is used internally by needs and get, but it's also used by find library and things like that. So the first time a kernel type of resource is looked up in the Paclet, that is the moment when the Paclet manager says, okay, before I load this Paclet, I'm going to look to see if an update is available. So there's no issue with part of the Paclet being loaded and then the Paclet manager later updates the thing. That the update is done before anything from the Paclet is seen. And the check for an available update does not touch the Paclet server. It's a fast check. It's just a few milliseconds to look to see if the Paclet manager believes an update is available. If so, download it, install it, but otherwise it will just load the Paclet and go on its way. It is possible to bestow the auto updating property on Paclets that don't have it because they don't declare it themselves, or importantly, they can't participate in the auto update mechanism because they don't have code that's loaded with get or needs, like a Paclet that has documentation only, or only front-end resources like a palette or something. Those Paclets cannot participate in the auto update mechanism because they don't, users never call get or needs or find library or anything on any of their resources. So there is a way to bestow this property, and we call this the Wolfram auto update mechanism. So what happens is that during kernel startup, Paclet manager consults a special Paclet called Wolfram auto update. That Paclet is kept updated by the Paclet manager itself. And that Paclet simply contains a list of packets that should be updated during startup. So this happens during kernel startup. It's a little background process that kicks off. It looks to see if any of these Wolfram auto update Paclets actually have updates available and they get installed. Okay, so now into some meaty stuff. So about loading of Wolfram language files. Paclets can declare that certain context should be loaded at kernel startup, or automatically when any declared symbols are first evaluated, or manually, the good old-fashioned way, requiring an explicit call to get or needs. So this is a very powerful aspect. People should understand this, right? And this is particularly relevant to internal developers that are extending the system via Paclets. So here's a typical example of a manual loading Paclet. Could say loading arrow manual. Now, of course, manual is the default, so no one ever puts loading arrow manual in their Paclet, but you could. And so this very simple Paclet, this Paclet info file simply tells the Paclet manager that when needs supermath is called, it should look for the supermath.wl file in the kernel subdirectory of this Paclet. Right? This is just your standard. It's like it's as if the Paclet's kernel directory was on $1 path. It's not how it works, but it's like that. So that's your basic Paclet. So manual loading is great, but we want to build the Wolfram system itself out of fully encapsulated Paclet components. For that to work, we need Paclets need to be able to do two things. First, they need to be able to both introduce and define system symbols. That's done with automatic loading. And then some Paclets need to execute some arbitrary code at kernel startup. That's startup loading. So automatic loading, which is actually easy to confuse with auto updating, right? They're not the same thing at all. They're totally different. Automatic loading lets us introduce system symbols defined nowhere else outside the Paclet and have the Paclet load code at the moment any of those symbols are first evaluated. This capability is not new. It relies on this package declare load functionality that's existed in the kernel for many years. But before Paclets existed, developers would have to put their package declare load calls into sysinit.m. And that really breaks encapsulation. Right? So if I had some Paclet that I wanted to define some system symbols and load lazily when their symbols are first evaluated, I could make just a component in the system, and then I have to put all the declare load call into the system.m. So I'd have to clutter up the system.m file with some code that was specific to my package. Luckily, you don't need to do that anymore. So here's a simplified package that uses automatic loading. Simply say loading arrow automatic. You have to name your context. And if you want automatic loading to work, you have to explicitly list the symbols that you want to auto load. These symbols should be written with their full context names, and they're written as strings. So that Paclet info file tells the Paclet manager to do two things at kernel startup. It will introduce those symbols, and it will set up definitions for those symbols that calls needs on the context to be called when they're first evaluated. So you don't, and there are a lot of Paclets use this. You don't have to, could literally create a Paclet that declares these system symbols. They don't have to be put anywhere else except in your Paclet info file and of course in the Paclet itself. All right. So what's nice about the automatic loading is that you can really fully encapsulate a piece of system functionality inside of a Paclet in a completely declarative way. You don't have to write any code for this. I just name the symbols, and I've now added system symbols to the system that there's no tentacles. I don't have to go into sysinit.m and add some special lines. I just have a completely encapsulated thing that extends the system in a very built-in way. It also allows the kernel to start up faster by delaying loading of files until they're first used. And that's actually quite important, right? One way to make kernel startup real fast is to MX everything, have the kernel just load all the MX files. That's what it does for the startup. It just loads every MX file during startup. And that's super fast because MX files load super fast. But they're kind of a pain. And we have, it's quite handy to use this lazy type of definition for system symbols. Right. So we actually have a lot of Paclets that use automatic loading. There's 169 Paclets in the layout that use automatic loading. So startup loading, that's a Paclet declare code that runs at startup. Should only be used to execute very small amounts of code that run. Basically, there are some Paclets that have specialized code they need to execute that doesn't work via the auto loading style because they need to have rules in the system that are present before a certain symbol is actually evaluated. That's really the main reason to use startup. So there's a simplified Paclet that uses startup loading. You notice there's no list of symbols in the Paclet info file because that's not relevant. We don't care what symbols the Paclet has. We're just going to. So this Paclet info file tells the Paclet manager to call get on that supermath.wl file at startup. Implementation detail is that context supermath is resolved ahead of time to the full path to the .l.wl file in the Paclet. And that is what the Paclet manager records in its own internal startup files. So the Paclet manager at startup doesn't have to look up files from Paclets. It just has a list. You load the following full paths, and it does that. So it can be as quick as possible. But there's only 7 Paclets in my system, and some of these are present in more than one copy. So there's only a very small number of Paclets in the system that use startup loading, which is a good thing. It's a specialized technique that you should only use if you're sure you need it. One example is keychain link. And it does that because it just needs to execute a few lines that look like this, right? It needs to set up, but it's something that needs to be set up for this system, this keychain link default system credential store set handler function needs to have this property defined on it, and it can't wait until that symbol is first evaluated. So it uses startup loading so it can run those few lines of code. Right. So the discussion so far has shown the loading property as a top level property of the Paclet itself. Okay, starting in 13.3, loading can now be specified as a property on individual kernel extensions. And this is an extremely useful and long overdue feature because it allows a single Paclet to have any combination of automatic startup and manual loading for different contexts. So an example of how this feature is useful is the keychain link Paclet we just talked about. It currently uses loading startup as a top level Paclet property. So it just says loading arrow startup in its Paclet info file. And then its context is keychain link startup, and that's the file. And what that does, so if Paclet this packet wants to use autoload because it has a bunch of system symbols that it declares, but it has to use loading startup because it has a few lines of code that have to run at startup. And loading was formerly a property of the entire Paclet. So the keychain link startup.m file basically just does the few lines of needed startup code, and then it has a bunch of code that manually sets up all the declare load definitions, all the stuff that the Paclet manager would do automatically for it if it was loading automatic. But now that loading is a property of can be a property of an individual kernel extension, keychain link could get rid of all of that complexity. It could simply say that for loading startup, load the keychain link startup context, and then it can use loading arrow automatic for all of this symbols that it wants to declare for auto load. So in this case, the keychain link startup.m file only needs the few lines of code that have to be run at startup, and then all the rest of the Paclet's code is just in the keychain link.m file, and the Paclet doesn't have to do anything to deal with its own auto loading. Okay, so some notes about automatic loading. Auto loading should really be used only for system symbols. The fundamental principle of the Paclet manager is that when a resource is being looked up like a context, what the Paclet manager does is it finds all Paclets that claim to provide that resource. It culls out any that don't match the current system, be the system ID or Wolfram version. And then it picks the resource from the Paclet that has the highest version number. So, as I'm always saying, version numbers in Paclets are critically important. And this is even the case for Paclets that don't have the same name, right? So if I have two Paclets in my system with different names that both declare the same context, and you say needs on that context, well, what's the Paclet manager going to do? It has to pick that context from one of the Paclets. They don't shadow each other by name, but they both have the same context. Paclet manager just says, okay, this is version 2, this is version 1, I'm going to take version 2. So how does the Paclet manager find resources? It turns out that the Paclet manager doesn't scatter files from Paclets around in places where the system knows how to find them. Rather, the Paclet manager hooks the system. So when the system goes looking for something, it asks the Paclet manager to find it. And so that's how it works. And really, most things that the system looks up go through the system find file function, right? This function is called for looking up libraries. It's called for looking up contexts. It's called for looking up files on, sort of path-based lookups. It's called for virtually everything that the kernel does to look up files. It's quite handy that they all go through this one function because the Paclet manager literally just hooks that function. So this is inside the, what happens when the system find file gets called. You'll see there's this, if has path prefix. This is basically saying, is this a full path? Starting from the root, then it just calls directly. It doesn't ask. The Paclet manager is not consulted for file lookups that are already fully resolved paths. But if it's not, we call this find file Paclet function. And only if that fails do we call a path-based lookup. So the Paclet manager gets first crack. And this is the one place, there's only one place in the kernel C code where there's a sort of call out to the Paclet manager. We just hook this one spot. And so this find file Paclet calls this function internal Paclet find file, which is defined in the manager.m file in the Paclet manager. So if you're curious how that works, you can go look at the Paclet find file function in manager.m. That is really the one sort of central place where most resources in Paclets are found. There are some other things that can't work this way, like because they don't involve a call to the kernel's find file function. Documentation lookups are an example. All in product documentation lookups go through the Paclet manager, whether you have docs installed or not. If you don't have docs installed, then Paclet manager constructs a reference.wolfram.com URL. So the Paclet manager is entirely responsible for looking up documentation. It's also responsible for calling search. Packet Manager does not implement search itself, but it is the place that it's the place that the search functionality is called. And then another thing is the front end resources. Front end, when the front end looks up palettes to put in the menu or something, it doesn't call the kernel. So the front end for Paclets, the front end things, the Packet Manager has to push information to the front end. So when you install a Paclet that has a palette, Packet Manager says, aha, this Paclet has a palette. It has to send some information to the front end to let it know that about this palette. Virtually everything else is done through that find file hook. All right, so some couple common questions. Get this all the time. Number one question I ever get about Paclets is like, hey, I just called Paclet install and it didn't install my update. I just put it on the Paclet server. Paclet install didn't find it. I think most of you already know the answer to this question, but it's easy in practice to forget. Is that when you call Paclet install some Paclet name, Packet Manager does not touch the Paclet server. That's much too slow. Paclet install has to be really fast if there's no Paclet to install, if there's no update to install. Packet Manager only looks at its cached information about what's on the Paclet server. Yeah, that cached information is kept up to date through various mechanisms, but as a sort of final fallback, every 3 days, when you start the kernel up, if it's been more than 3 days since you last got an update from the Paclet server, it will update all its information about what packets are available on the servers. There's other times this gets updated as well, often kind of once in a session. This packet site update happens in the background. So you generally are not really that far out of date with Paclet servers, right? So when you push out a Paclet update, your users it will sort of trickle out over the next 1 to 3 days to users. But if you really want to be sure that you're getting the absolute latest version, because you just pushed an update, then you call Paclet site update. Yeah, update the cache. Or you can say Paclet install, and you can use the update Paclet site's true option. So just remember that the Packet Manager does not touch the Paclet server on operations like Paclet install. If it doesn't know about an update being available, you won't go and ask the server. That's just too expensive. All right, and then finally, what's this Packet data rebuild function, and when do I call it? Packet data rebuild calls the Packet Manager. It's an expensive call. It scans all the Packet info files that it knows about in the system and rereads them all and rebuilds all of its internal data structures about what Packlets are present and what they contain. You don't need to call Packet data rebuild if you're only performing Packet Manager operations like Packet install, Packet disable, Packet directory load. The Packet Manager is responsible for maintaining its own state during Packet Manager operations. So you don't need to just blindly call Packet data rebuild if you're doing normal things with the Packet Manager. But you absolutely need to call it if you're making any kind of modification to the Packlets outside that the Packet Manager doesn't know about, like you're hand editing a Packet info file, right? Or you manually hand copy some Packet into your Packet repository locally, right? Packet Manager doesn't realize that this packet has been added, or it doesn't realize that you've added some new context to your Packet info file. In those cases, you do have to call Packet data rebuild.